You walk across a bridge, and it holds your weight without a second thought. But inside the steel, a fierce, invisible struggle is happening. Let's look at a classic, simply supported beam. Back in 1750, Euler and Bernoulli realized a beam doesn't just sit there, it actively fights back. It resists being sliced in half by shear forces, and it resists bending into a U-shape through internal moments. Back in 1750, Leonhard Euler and Daniel Bernoulli discovered a hidden mathematical language inside solid beams. They realized that bending and shearing aren't just random forces, they actively drive each other. Here is their genius insight. If you graph the bending moment along the beam, the steepness of that curve, its slope, is exactly equal to the shear force at that exact spot. This gives us a brilliant shortcut for finding a beam's weakest point. Because of calculus, when the shear force drops to exactly 0, the bending moment hits its absolute maximum. Imagine dropping a heavy safe right in the middle of a beam. This is a point load. The shear force snaps instantly, creating a sharp vertical jump. Because of that sudden shock, the bending moment builds in a straight line, peaking at a sharp kink right under the weight. But real-life loads usually aren't that focused. Think of a thick layer of snow covering the whole roof, a uniformly distributed load. Now the shear force doesn't snap, it slopes down gradually. And the bending moment? It curves into a beautiful, smooth parabola. Notice the secret calculus connection here. Whether it's a sharp kink or a smooth curve, the beam's bending moment always hits its absolute maximum exactly where the shear force crosses 0. That 0 crossing is the beam's most dangerous spot. After all that intense calculus, structural engineering often boils down to 2 golden cheat codes. If you drop a single heavy weight right in the middle of a beam, the maximum bending moment is P times L divided by 4. But if you take that exact same weight and spread it evenly across the whole length, the maximum moment drops significantly to WL squared over 8. But here is the reality check. We never actually design a beam to just barely survive that maximum moment. We build in a massive buffer. In the US, the 2024 AISC standard demands a safety factor of 1.67. Meanwhile, European codes scale up specific loads, adding 35% for the building's dead weight and 50% for live loads like people and furniture. Because in the real world, materials aren't perfect and people always bring more stuff than they promised.